In this video, we'll get some practice defining list processing predicates in Prolog, starting with the contains predicate. So contains x comma L is true if item x is in list L. Okay, so the idea behind contains is we want to CDR down or traverse through this list looking for the item x. Checking each time through, is the item at the front of the list? If not, then we're going to recursively ask contains if the item is in the tail of the list. Eventually we'll run out of items if it's not there and the whole thing can return false, or it will be at the front of the list at some point and we can return true. So base case in this case is that the item's right there at the front of the list. So contains x, x pipe, don't care. So the idea here is we have this list, so this list L is full of items, but the very first item is the same value as the item we're looking for. So whatever value gets into this key slot here goes as or happens to be the same as the front of the list, then that's just true. It's done right away. So if X is the first item of the list, great, success. That'll match with this fact and it will return true. Otherwise, what we need to do is check, is it somewhere else in this list? So we need to create a rule. So contains X, some list. We could say head, pipe, tail here. Now we don't care about the head now because we've just checked that it's not going to match X, so we can actually say don't care here. And then instead of having a fact, we're going to create a rule. Contains X, the tail now. So we want to ask, is this actually in the tail? Contains X, T. Okay, so if we pass in the list 1, 2, 3, and the value we pass in here is 2, then it doesn't match the front of the list because 1 doesn't match, 2 doesn't match 1. So what we'll have here is this rule where we have the key 2 and the list don't care pipe the rest, which will be 2, 3. And we'll ask, does the list 2, 3 contain the item 2? In that case, it will be true. So let's test this out. So reconsole this is lists.pl. We could just ask a simple query like contains the list, does it have A in the list 1, 2, 3, A, B, C? And that's true. And if we want, we can trace this real quick just to see that it's CDRing down. Trace, ask that same query. So it asks, does the whole list contain it? And then if we creep, then it asks, does the next list contain it, or the tail of that list? Does the tail of that list and the tail of that list? Eventually, A is at the front of the list, and the whole thing returns true. Okay, let's see here. Alternatively, we could do something like, say, contains Z, the list 1, 2, 3. There's something short, so it eventually gets to the end. So obviously that's not going to match our base case because Z does not equal 1. And we creep through, it's not in the next base case, it's not the next element of our list. And we ask again, is it in the tail? It's still not. And then we get to this point where we're asking contains empty list, and it returns false. Notice in this case it doesn't end up going into the rule. The reason being, both of these clauses, so the fact and the head of this rule, both have an assumption that there's at least one element in the list. Remember, the structure H pipe T, or something pipe something, assumes that there's at least one atom in that list, one element, and then the tail can be anything. It could be the empty list or the rest, but there has to be at least one element in there. So if we're trying to unify contains Z empty list, neither of these will unify with the empty list. So it won't match our fact, it won't match our recursive rule, so then it can't match anything and says, well, then it doesn't exist. So notice we didn't have to code the failure cases. We could just run through the list as we have it, and then when it reaches a failure case, there's no fact or clause to support it, so then Prolog automatically assumes that it won't work. All right, no debug. So that's the contains predicate. Let's try another one. Length. So len of some list is some length is true if length is the number of elements in the list. So the first term should be some list, the second term should be some number. And this will return true if we provide both of those, but if we provide an empty list, or sorry, an empty variable here for length, it should supply the actual value of that length. So the idea behind this predicate, similar to how we solved this similar problem in Scheme. So we went through and we said just CDR down and count the number of times that we can do so. So a base case in that case would be if we have an empty list, then the length is 0. So we already know that one without doing much work. Otherwise, there's at least one item in our list, so we'll say len h pipe t will unify with at least one item, and then some number n that will eventually be our result. So what we can do is then ask what is the length of the tail of this list. Call that m, just to be some other letter, and then add 1 to that, so n is m plus 1. So if we pass in an empty variable for the length, that will unify with this empty variable, and that empty variable will get filled with the length of our tail plus 1, where the length of the tail is determined by recursing through, and then asking the length of its tail, and asking the length of its tail. Eventually, having an empty list will return 0, and then the item before that will be 0 plus 1. Now return 1, and then we'll come back up. That n will unify with this m, and add 1 to it again and again and again. So CDRing down, we figure out what's the length of the tail, add 1 to that, and that's the length of our entire list. So no debug is already on, so let's reconsult lists. There it is. And let's just ask a simple one like the len of the list 1, 2, 3, 4 is x. Len 2. Did not save. There we go. Try it again. Singleton variable h. Can fix that in a second. Yeah, so we got the len of these 4 elements gives us 4. Now the singleton variable warning here is because this variable h never gets used, right? So the idea behind this recursive case is ask for the length of the tail and then just add 1 to it. It doesn't matter what the actual value in the head of that list is, so we can just put a don't care variable, and then Prolog won't yell at us. There we go. We can also use this reversibly. We can ask, is the length of this thing 4? And that will return true. Or we could ask, is the length of this list 3? And that will return false. So 2 different ways we could use this. Forward asking what is the length, and sort of a backwards asking, is this the length? All right. Now, this is a recursively defined operation, right? The recursive call is not in a last call or a tail context. So when we make that call, we still have to hold on to this activation record, so to speak, in order to later on do these deferred operations of adding 1 to the sum of our tail. Sorry, the length of our tail. So what we can do to try and make this iterative, or one naive approach to this, let's just create len. Copy all these things, and we'll call them len it, len underscore it. So one approach to, or perhaps a naive approach to making this an iterative solution is to reverse these 2 things. So if I say put this here and put that there, now the recursive call is happening in a tail context. And from a declarative point of view, what we're saying is still the same sort of thing. The tail of our, the length of our list is 1 more than the length of the tail of this list. But let's see if this actually works. So save, reconsult our knowledge base. It loads fine, but if we ask len it of the list 1, 2, 3, 4 is x, we get an error. Arguments not sufficiently instantiated. So what happens here in our recursive case, it takes the tail out of our list and then says add 1 to the variable m. But we haven't yet defined what the variable m is. That happens in the next clause. So unfortunately, due to the imperative meaning of these processes, we can't just flip the order here and let the declarative structure take care of it. We do have to, unfortunately, make sure that all of our variables are instantiated before we do arithmetic on them. So in this case, m doesn't have a a value before we run the recursive call. So a better approach is to add in an extra variable, as we typically do with these iterative approaches. So we'll say len it of L and R, so of some list is some result, and then we'll pass that to a helper function, len it, that takes in the list, the current value, our accumulator value, and then the final result. Okay. And then a sort of thing happens where we take this value and we're going to add 1 to it every time where we recurse through. So our base case is that we've run out of items still, so it's still the same condition that the list is empty. And in that case, what we'll do is we'll take the running total so far, and we'll unify it with the global total. So if these two slots have the same variable, then they have to have the same value. And since this last one will always be empty until this case, so we're passing in an unbound variable, then what we'll do is we'll end up unifying it with the accumulation variable in the middle here. Okay. So then the recursive case is going to look a little bit different. Let's actually just delete this and start from scratch. The recursive case says we have some list. We don't care about the head still. We do need the tail still. That has, we've counted so far some number of items up till this point. And then R is still an unbound variable that we're going to unify with later. What we'll do is we'll take the current counter, C, and we'll say C1 is C plus 1. And then we'll do another step. So len it is the length of the tail, gives us C1, or pass our C1 into it, and then get back the result. So if our counter starts at 0, each time we recurse, we're going to add 1 to that counter. And when we get to an empty list, then we'll take that counter and put it into the result variable. Now the result variable R here is unbound coming in, unifies with an unbound slot there, which unifies with R here and then here. So we're never actually unifying R with anything until this very last step in our base case. At that point, it takes the accumulator value and puts that into R. So this last slot will unify here, which unifies back, which unifies all the way back to the original call. So save this and try it again. Got lists. And let's see, len it, let's just do the same, 1, 2, 3, 4, x, and then that works. Okay, so there's the iterative approach. Again, we need some sort of helper so we can have the extra variable in there, and then we can pass values forward rather than trying to pull values back from the base case. All right, for our next approach then, for our next problem rather, let's solve the join objective. So join list 1, list 2, list 3 is true if the first arg joined to the second arg makes the third. So L1 plus L2 gives us L3, where we're assuming all three of these things are lists. Okay, so this is essentially just the append behavior. We need to take all three of these things, which are a list, take all the elements out of the first and second one to make the third list that has a flat list with all of their elements combined. So this is a bit of a recursive approach, but what we'll do is we'll take the elements out of the first item one at a time, creating sort of a deferred cons there. So we take the head off the list and we say join what's left, the tail of L1 to L2 to make L3. And then we'll keep doing that until L1 is empty. At that point, we're saying join an empty list to L2. So the result then, the L3, for joining empty list to L2, then L3 is just L2. There's nothing else to add to it. So we can just take the value from here and put in there. And then on the way back through the recursion, all those individual elements we took off will join on to the result that we got from our base case. So our base case, join some empty list to L gives us L. So join an empty list to a regular list gives us that regular list and nothing else. And now our recursive case is a little bit more involved. So we're going to split the first list. So we're going to say h pipe, we'll say T1 for the tail of list 1. List 2 we don't need to do anything with. It's just going to sit there until the very base case and then it'll get carried over. So just list 2 here. And then this last structure I'm going to explain in a second, h pipe T3. So this says take this h here and unify it with T3. But we'll see how that makes sense in just a second. So what we've done here so far on the way forwards through the recursion is we've split L1 into two parts, the head and the tail. For now, we don't care about the head. We're just going to recurse on the tail. So we'll say join the tail of list 1 to L2 to get something called T3. Okay. Now, if T3 is the result of joining everything in the tail of list 1 to list 2, then T3 has, let's say, all the elements except one of those elements. Then what we want to do is join that one element, H in this case, to T3. So that says the unification, or sorry, the result variable that we passed in, R, will unify with this structure, where T3 is everything but the first element, and we're saying cons H to that. So cons the first element to everything else means our result variable will unify with that entire structure. Right? If I say R equals 1, pipe the list 2, 3, 4, then R is just the list 1, 2, 3, 4. So if I'm passing R in as my output variable when I call join, then H in this case would be 1, and T3 would be 2, 3, 4, everything else. And it says unify everything together and call that our result variable. So we get the flat list 1, 2, 3, 4. Okay. So let's walk through this. This is a bit of an involved construct. So let's actually see how it looks. Let's save lists and run. Simple join to start with. Not particular. Let's just do this one. Join. Let's actually let's just run one first. Join 1, 2, 3 A, B, C to get R. And that says R is those two things together, as we kind of expected. But let's do a trace first, and then ask that same thing. So trace says walking through each one of these lines. So in this case, 1, 2, 3 is going to unify with. It doesn't unify with an empty list because it has elements in it. So it's going to unify with this construct where it says H pipe T1. So the value of H is 1, and the value of T1 is everything else, so 2, 3. Okay. Now L2 will unify with the list ABC, and R here will unify with this structure, H pipe T3. I'm actually going to write this down so we can keep track. Okay, so we said we have H here is going to unify with 1, T1 will unify with 2, 3, and well, we had L2, which is going to unify with ABC, and then R, I was going to suppose do it this way, H pipe T3 unifies with R. So this is the stuff we're passing in, 1, 2, 3, ABC, and R. Okay, so R is going to unify with this construct, but we don't know what this is yet. We know what H is, so technically we could replace this with 1 pipe T3, but we don't have a value for T3 yet. So in order to do that, we continue on with the body of this rule, which will eventually yield the value for T3 so that we can combine those together. So that's the first step. So then the recursion says call join on T1, which is the list 2, 3, L2, which is the list ABC, and T3, which is, again, an unbound variable. So the next time through, we get call this H prime just for the second time through, joins with the list 2, or sorry, the value 2. T1 prime joins with the list 3. And L2 doesn't change, it's still ABC. Right, we passed L2 from L2 to L2. Okay, and then this last one here says T3 unifies with this construct here. Sorry, this should be L2 prime, I guess, even though they're all going to be the same. This construct here is going to unify with T3, so we get H prime pipe T3 prime, let's call it, unifies with T3, where H prime we already have a value for is 2. But we don't have a value for T3 prime, a new instance of this variable the second time through the recursion. So we go through again because the recursive case just says call join. So we get H double prime gets the head of this list, which is 3. T1 double prime gets the rest of this list, which is the empty list. L2 double prime is the same list as it always is, ABC. I suppose I could have been tracing this, but oh well. And the construct HT3, oops, let me delete that, copy, where these are now the third instance of these, so H double prime and T3 double prime unifies with this T3 that we passed in. So that's T3 single prime. Okay. Now, almost at the end here, when we get to the bottom here, we say, we call this one more time with T1, where T1 is the empty list. Now that's going to unify with this case, right? Because if the first thing we're passing in is empty, that will unify here, where L here can unify with anything, and L here can unify with that same thing. So we have the empty list unifies with the empty list, right? Because we're passing in the empty list as T1. And then we have L here will unify with what we passed in as L2, which was ABC. Okay, and then this last part here, which is also L, is going to unify with the variable that we passed in. So we passed in T3 double prime here, so we get T3 double prime. Yeah, so this T3 double prime is what we passed in as this third term here. Notice it's not yet bound, but L already has a value, right? So that means that T3 double prime equals A comma B comma C equals T3 prime. Something like this, where this is what we passed in, so that's going to unify with L, which got a value from this second column here. So T3 unifies with L, but because L unified with L2, that means T3 is unifying with that L2 value. But now T3 already has been used up here, where H triple prime we had a value for was 3, and now T3 double prime, it might be easier if I type all these down one last time here. So we had, just to walk through this, we had R equals list 1 pipe T3. We had T3 equals the list 2 pipe T3 prime. And we had T3 prime equals the list 3 pipe T3 double prime. And we had T3 double prime equals L equals ABC. Let's say L2, just so we can remember where that came from. Okay, so if T3 equals the list ABC, that means we can take that list and put it here. Okay, which means all of that can go into here, 3 pipe ABC, which means 2 pipe, 3 pipe ABC can go into here. So we end up with something like R equals 1 pipe, and then 2 pipe, and then 3 pipe, and then the list ABC. Close, close, close. Okay, which, as we've seen before, is just 1 cons 2 cons 3 to the rest of this list, which is just the list 1, 2, 3 ABC. Okay, so this construct here might seem a little bit strange. It's essentially saying do this part last, unify some empty variable with this structure, which says take the result variable T3 and cons on H1. If you want, you can use a slightly different structure, where instead of doing that up here, we just say this is R, we can call it that, and we can say down here R equals H pipe T3. Might be a bit easier for forward-thinking people, where we unify T3 with a value, then we join H and T3 together, unify that with R, and then that gets passed back. You do need to be careful about this, because there are situations where this doesn't quite work the same, because now we're unifying anything with R instead of something that has to be a list with exactly one value. But generally speaking, those two things mean the same thing, just a slightly different structure. All right. Let's walk through this trace. It should mean pretty much the same thing. So in the forward case, we're just removing things from join and calling join on a smaller list. So removing things from that T or from that L1, and we're saying join the tail to the rest of L2. Okay. Eventually we get down to the empty list. And the empty list, this structure says this will unify with empty list, this will unify with L2, and this will unify with our result variable. Now because these are both the same variable though, then both of these things have to have the same value as well. So when we join that, we get ABC in both slots. All right, and then on the way back up, all we're doing is consing this H into our results. So we can see 3 gets joined onto the result, 2 gets joined onto that result, and 1 gets joined onto that. And we get the final answer. All right, that's the joining two lists. Now it's worth mentioning this join can be used in a bunch of different ways as well. We can see it to just be a merge here, where we append two lists together, but we can also use it in reverse to get parts of a list. So I can say, for example, join 1, 2, 3 to something to get the list 1, 2, 3 ABC. And that's only true if that something is the list ABC. We could do it the other way as well. We could say join X to the list ABC gives us the list 1, 2, 3, ABC. So it's asking what can we join to ABC to get the list 1, 2, 3, ABC, and that of course is the list 1, 2, 3. And we can also use it to decompose a list. We can say something like join L1 to L2 to get the list 1, 2, 3, ABC. Now, there's a bunch of different ways that this combination could be true, right? It could be true where L1 is an empty list and L2 is everything, or if we backtrack, L1 has one element and L2 has everything else, or L1 has two elements, and yeah, so it's all the possible combinations there. All right, we can also do this using, we can also use membership, use join to construct the membership predicate, where the idea being is we're asking, is there some list we can join to an item, join to some other list in order to make this result? So if we want to know membership, is there an A in the list 1, 2, 3, ABC? We could say join something to the list that starts with A and has something else in there. That gives us the list 1, 2, 3, ABC. So now this is asking, is there any way we could fill in these values, these empty spaces, such that A is surrounded by values in here? Now notice this could be the empty list, or this could be the empty list, so A doesn't have to be in the middle. It could be at either end as well with this construct, and we get the membership predicate essentially. All right, let's move on then to the next example. This one's out of the notes here. Del first. A lot of notes in there. Okay. Del underscore first x comma L comma R. This is true where R is the result of removing the first instance of X from L. So L is a list, X is some item that might be in that list, R is the list that has all the elements from L except the first instance of X. So it kind of plays out like we're going to CDR down this list until we reach a base case, where that base case is that the item is at the front of the list, kind of like with our membership predicate, or what was it, contains predicate here. So our base case is similar to this, is the item in the front of the list, but now we have to sort of create a result there where we're taking everything except that first item. Now as we're CDRing down, we're going to be removing items from L so that we can continue to look for this item X. But once we've found it, we're going to return the tail, so everything but X, and cons all of those items that we removed back onto it. So it's very similar to the contains, but with a consing back on pipe operation, similar to what we just saw with join. So our base case, del first X is at the front of some list. Okay, so if it's at the front of the sum list and we found it, that's great. Then all we have to do is put a tail in there, return the tail. If this was the starting point, if somebody had queried remove 1 from the list 1, 2, 3, well then we can just return the list 2, 3. So just return the tail of the current list. Now, if we had to dig down the list in order to get there, we're going to have to cons those things back on. So we need a recursive rule as well. Del first, looking for some key here. Now we're going to want to split this list apart. So we want h pipe t to remove things every time. To remove things, and then we also want to cons that h back into our result. So we're going to get some sort of result variable here. It's going to be a rule. Some sort of result variable here, but we don't just want that result. We want to have h joined onto that result as well. Now, how do we get that result? Well, we're going to del first from the tail of the list. If we're in this case, then we're assuming that x is not equal to the head of the list, so x does not equal h. Okay, rather assuming, we'll assert it. And then if that's the case, then we're just going to recurse. So we're going to say del first, remove x from the tail of the list, yielding the value r. So if we want to remove 2 from the list 1, 2, 3, 4, it's not at the head of the list, so we'll ask to remove 2 from the list 2, 3, 4. We'll get back the list 3, 4, and then we'll join the value 1 back onto the front of that. So we end up with 1, 3, 4. All right, let's try this out. So del first, reconsult, and del first, let's remove the first A from the list A, B, A, C, A, D. Okay, and that returns BACAD, so it remove the first A. If we backtrack, there's no other first A's. It only removes the very first one. Okay. Now, the next query is very similar, the next predicate is very similar to this first one. Instead of just del first, we're going to say del XLR. And this is true where R is L with any instance of X. So where R is the result of removing any instance of X from L. So not necessarily the first one, it could be the second, third, or the last. Could also be the first one as well, though. All right. And this actually is coded very similarly. So if the item's right at the front of the list, then that's easy. So we can say if X is at the head of our list, then we'll just return the tail. Great, no problems. Oh, sorry, not del first, just regular del. And otherwise, we're going to recurse through. So we're going to say X, we're going to take the head off of our list and get some sort of result variable, but we're going to attach that head back in there. H pipe R, there we go. And the recursive case is just going to say del X from the tail yielding R. So it's actually pretty much the exact same as del first. The only key difference here is that we're not going to explicitly prevent X equaling H. So let's say here, or not equaling H rather. So if we call this back lists and we ask del, this exact query actually, minus the word first, it gives us the first answer, but then if we backtrack, it will remove the second A, or if we backtrack again, it removes the third A. If we backtrack again, there's no more A's, but it removed each individual one. So the question is, why does this one line, X does not equal H, change the behavior from only removing the first item in our list to removing any item in our list? And the answer is backtracking. So notice both of these predicates with the same query ran into the same first answer, right? The A was at the front of the list, and that was it matched this base case. And we had the same base case in both predicates, so we got the same result. So if the item's at the front of the list, just return the tail. And that's true here. We return the tail BACAD, or here we return the tail BACAD. Now, what happens next is we said backtrack. So if the item's not at the front of the list, then if the item was at the front of the list, it hit this base case. But if we say backtrack, then we're saying, well, don't use this base case. Try the rule case instead. So undo this unification and try unifying with the head of this rule. And it will match the head of that rule, where X is the item we're looking for. This list is the list that we have, where head is equal to X in this case, because we're looking for A in both of these cases. And then the result is the result. We'll talk about that when we get to it. So if X does equal H, in this case, they're both A, then this yields false, which means the rule no longer applies. So it says if you hit this and X and H have the same value, then this is false. So it has to backtrack and says, okay, well, I tried to satisfy using this rule, but that didn't work. There's no other rules, so it fails. With the regular del case, not del first, it doesn't have that. So if X equals H, if they're the same thing, it doesn't matter. It just pulls it off and calls recurse. So in the first instance, it matched our base case and it said, okay, return just the tail. We said backtrack. It says, okay, well, what happens if instead of removing the head and returning just the tail, I keep the head, I attach it to the result, and I call delete from just the tail. So it says take this value and delete from there. Eventually that reaches the base case again when it hits the second version of A. So that's the A between B and C here that's no longer in the second answer. At that point it hits the base case and says, okay, well, I've removed it successfully from here. And then we ask you to backtrack again, and it says, okay, well, if I didn't remove that one, then I'll use this rule where I keep that one, and I'll try removing it from the tail from here. And it finds the third instance of A, this one here, and says, well, I can remove it there as well. So having that one extra clause in there, the X does not equal H, prevents backtracking when we say this succeeded but backtrack anyways. It prevents backtracking from using this rule for that specific case, so we get very different answers. And notice also we don't fall into an infinite recursion. For example, if the item's not there, del Z from the list ABC is R. it just tells us false. So it doesn't fall into an infinite recursion, constantly trying to remove items. And again, we didn't have to code for a failure base case. The idea being each time through, we're going to remove an item and call del on the tail, which is going to mean our tail is getting smaller and smaller and smaller. If it never reaches our success base case, then it will never unify. Sorry, eventually that list will be empty, and then it won't unify with either of these cases, because in both of these clauses it says there's at least one item, and it says so in this predicate as well. There's at least one item. So the empty list just doesn't unify with a list that has to have one item, and Prolog returns false. All right. Also worth noting, this del predicate can be used backwards as well. We can say del A from B, C, D, A, E to get R. So remove A from our list. That gives us the forward usage. But we can also sort of flip these and say del A from some list to get B, C, D, E. And that says, well, that's true if A is at the front of the list, or in the second part of the list, or the third, or the fourth, or the fifth. There you go. So we could use any of these 5 lists to make this statement true. So Prolog can find all 5 of them for us. All right, that's the end of this video. In the next video, we'll take a look at some more practice using these list processing predicates in Prolog.